Okay, guys. This is going to be about magnets, and it's going to give you hand cramps. You'll see why shortly.
Hand
cramps. We'll do some physics gang signs today.
Yay, the gang signs.
Okay. Like I said, it'll make sense shortly. Okay. This is something hopefully you guys have learned in the past. Likes repel, opposites attract for magnets. So if you bring two north poles together, it repels. If you bring a north pole and a south pole together, they attract. Everybody remember that? Everybody had the experience of at least putting magnets together and feeling the repulsion? Alright. The first confusing thing that just kind of will bother you because it doesn't make perfect sense is the Earth's magnetic field. The Earth's geographic north pole is actually the south pole of the magnet. And vice versa for the south pole of the Earth. How you want to think about it is the north pole of the Earth is what the north needle on the compass points to. So the north pole of a magnet points toward the north pole of the Earth. So in order for them to be attracted to each other, the north pole of the Earth has to actually be the south pole of a magnet. Does everybody understand that?
Yes, sir. Yes, sir.
Okay. Okay. Magnetic field lines always point from north to south. So they go out of the north pole into the south pole. And magnetic field is the strongest when their lines are closer together, so they're going to be stronger here, they're closer together, instead of out here where they're further apart. And the symbol B is used for magnetic field. And magnetic field is measured in Teslas. And it's abbreviated capital T. And it's nice that the symbol B is used because it makes perfect sense. Okay. Magnetic domains. Some of you guys have talked about this before at any point. Magnetic domains. Okay. So magnetic domains are these tiny little things inside of materials. Normally they point in random directions. If they're all lined up and permanently all lined up, then you actually have a magnet. If they are there and can move freely, then you have a material that can be attracted to a magnet. So what happens when you pick up a paper clip with a magnet? The magnet looks like this, and when it touches the paper clip, it causes the paper clip to look like this, and all the magnetic fields line up. So when you're touching that paper clip with a magnet, the paper clip then becomes another magnet, so you can pick up another paper clip. Does that make sense?
Yes, sir. Yes, sir.
So materials that can be picked up by magnets, that are attracted to magnets, have domains that can move. Materials that cannot be picked up by magnets have domains that are stuck in place. Alright, here you go with all the hand symbols. Okay, all magnetism comes from moving electric charge. So whenever electric charge is moving, it generates a magnetic field. So like in a magnet, what happens is all those magnetic domains line up, and those magnetic domains are there because of electron spins. That gets a little complicated when you talk about the atomic nature of magnetism. It's much easier to think about it in terms of like protons and electrons moving in current. So when you have a current carrying wire, it generates a magnetic field around it. And it generates a magnetic field around it by what we call a right hand rule. So what you do is you take your right hand, point it in the direction the current's moving. So in this case, I is going this way. And then your fingers wrap around in the direction the magnetic field goes. So if you look at this, on the left side of this wire, the magnetic field is coming out of the board. And on the right side, it's going into the board. So you put your thumb, you line your thumb up with the wire, and your fingers wrap around to make the magnetic field lines. Does that kind of make sense to everybody?
Yeah. Yes, sir. Yes, sir.
That's not even that bad yet, Kyle. So out in front of it, it's pointed to the right, and behind it, it would be pointed to the left. Does that make sense to everybody?
Yes, sir. Yes, sir.
Okay, we're going to do some practice with this now. So we have the current's going one direction, and we're looking for the magnetic field at the X. So take your right hand, point your thumb in the direction of the current, and which way is the X going? Or which way is the magnetic field going at the X? Towards you, so out of the page.
Out of
Does that make sense to everybody?
How do we know
Yes,
it's
sir.
down?
How do you know it's not like this? So like, what we do is we take our thumb pointed this way. So on top it's going out, and on bottom it would be going in.
Oh, this is just always?
No. just in this case. So, do you see how, take your thumb, line it up with the current?
Yeah.
So do you see how my fingers are pointing out above it? If I take my thumb and put my fingers below it, now my fingers are pointing in.
Okay.
That makes sense? Okay. There are a couple more examples of this. Hopefully they'll start to make sense here. Okay.
There we go, I got this one.
So now, okay, Sarah, let's work through this one together here. Alright, take your right hand, point your thumb down. What are your fingers doing on the right, when they're on the right side of your thumb? Are they going into the board or out of the board? Into the board. So this one's into the board.
Just for the X.
Just where the X is. That make sense, everybody?
Does it have to be right hand?
For current, it has to be a right hand.
Okay.
The first one, this one was out of the board. So I see the X is,
like lined up.
what? Your thumb's pointing the wrong way. So it
And has to always.
has to point in the direction of the current. Okay, number 3 here. Why don't you guys try to do this one on your own so nobody yell out the answer quite yet?
Was 2 out?
What was 2?
Wait, 2 is into the.
Okay,
Oh, I'm sorry.
what is this one into or out of the board?
Out.
Out of the board.
Ow, it's on the bottom.
Your fingers are pointed out right now.
Yeah,
Or-
put your thumb in the direction of the arrow. Laura, you should
You have to curl your fingers in.
It's a circle around the direction your fingers.
Okay, how are you guys doing?
Good.
Everybody understand why it's out? So it's thumb pointing that way,
Good job.
hand curls that way.
1, 2.
Okay, why don't you guys try this one again? Try it on your own and then I'll talk about it so nobody yell out the answer.
I told you it was
Yes.
I got you. Get a curl.
This is great.
Okay, into the board or out of the board?
Into.
Into. Thumb that way.
Oh, I think it's the wrong hand.
Make sure you got your right hand.
I hate when I mix up my hands.
I see what you did there.
Alright, remember the right hand does not make the L.
It's the right hand.
Okay,
I was
It's
right
backwards L.
good job.
When does the L go? Yeah,
Okay. Everybody feel okay about finding the currents and things like that? Okay. There's more of this too,
Wait,
so.
I have a question.
Yes, Brian.
How do you, like, you know,
Guys, shh.
if you go like this, it's going in, but if you go like that, it's going out.
It matters whether it's on top or bottom of the wire. So in these problems we were doing, it mattered where the X was.
Oh.
So in this one, it's going in because we're looking at on bottom of the wire.
That makes sense.
If we were looking on top, it'd be going out.
Thank you.
Okay. So whenever you have a current carrying wire in a magnetic field, it experiences a force. This is how like all motors and generators work, and we'll talk about that a little later on. But so you have current carrying wires, put it through a magnetic field, like between this horseshoe magnet, it's going to experience a force in one direction. And this is going to be a right hand rule as well. So you want to make sure you keep your right hand going here. Alright. And not only will a current experience a force, but if you just have a charged particle like a proton or electron in a magnetic field, it will experience a force as well. So this is the other right hand rule. I don't like... Okay, I don't like this one because it makes my hand cramp when I try to like do all sorts of weird stuff with it. Let me show you guys an alternate way. So this one is the force is your thumb, the current to the charged particle is your pointer finger, and the magnetic field is your middle finger. I think an easier way to do it to avoid getting your hands cramped, you may want to write this down. Hold your hand like this. Your thumb points in the direction of the current. Your fingers point in the direction of the magnetic field. And your palm points in the direction of the force.
So Sarah needs directions.
What is this one?
Repeat.
Okay, so again, you can do it whichever way you want. But like I said, this way will make your hands cramp a little less. And this is the way I'm going to be doing it. So, fingers are magnetic field. Thumb is current. And the direction your palm points is the force. So, like if you think about an arrow coming out of your palm, that'll be the force. Okay. Alright. Now, the one thing that gets a little bit confusing, your right hand is for current or positive charge. Your left hand is for electrons.
I feel like I'm using right hand.
Okay. Right hand is for positive charge or current, because current is, remember, we assumed it's the motion of positive charge. Your left hand is your, for electrons or negative charge. Everybody okay with that?
Is this physics or like sign language?
How are you
A little bit of both.
How do you know if I have a question about this?
Why are you hating?
I'm never answer your questions anyway, Brian, so it'll be fine.
Oh god.
Okay.
Everybody's hating me.
Shh, guys, quiet. Alright. So for reference, when you see an X, it symbolizes something going into the board or into the page. When you see a circle with a dot in the middle, that's something going out of the page. It's just something you kind of have to remember. Alright, so let's do a bunch of examples of these. Okay. So, take your right hand. Thumb points in the direction of the current.
Oh god.
That's not comfortable.
We're in the middle of a studio session.
Okay, so thumb points in the direction of the current, fingers point down in the direction of the magnetic field. What direction is the force, into or out of the page? Into.
Stand up.
Because you went with the.
So into the page for that one.
Can I go like that?
It would be so.
You can contort your body however you see fit, Chloe.
Okay.
Just don't poke like Carrie in the eye or anything like that.
Throw those.
Yeah.
Going up in the
So would it go like this?
It's into the board.
You know that?
Oh,
You know that
it'd
because
be
of
like
this
this.
thing, right?
No.
First wall.
Okay. Shh, guys, quiet. Let me explain it again real quick. So for the right hand rule with the force on a current carrying wire, it's your thumb goes in the direction of the current. So the current's going this way, so my thumb's going this way. Fingers point in the direction of the magnetic field, which is B, which is pointing down. And then my palm points in the direction of the force, so into the page.
Oh, so that will tell you.
That'll tell me where.
Can you show us this way? How this way?
Do this. I'm not going to show it both ways each time. Okay. Next one. So we have magnetic field. These little dots mean out of the page. So when you see the circle with a dot in it, that means out of the page. Current's going this way. So take your right hand, point your fingers out of the page for the magnetic field. Thumb to the left for the current, and force is up because your palm is up.
I'm confused about how you know whether it's
So it's.
Okay, so thumb always has got to go in the direction of the current. Fingers got to point that way for magnetic fields.
how do you know it's going to be?
Does it matter?
The circles with dots in them mean the magnetic field's going out.
Wouldn't it be down? The force be going down?
No, magnetic field's going out of the page, Kyle. So flip your hand. Okay. Your fingers have got to be pointed toward the back. There you go.
You're carrying a tray.
So the easiest way to do this one is to go like that. Okay, any questions about this one? Do you guys feel like you're starting to get this?
Yes.
Is there one that's more comfortable to do?
No, none of these are comfortable, to be
All right.
honest. Okay, why don't you guys try this one on your own, so nobody shout out the answer here.
What are we going to do like, during a test?
Poke each other in the eye.
Maybe like giving each other a standing
Why can't we just like do all problems like
Hey,
this?
Okay, so is this into or out of the page? Into. So it's into the page. Put our thumb up because current's going up. Fingers go to the right because magnetic field is going to the right, and our palm points into the page.
It's easier if you do it.
Make sense?
Yeah.
Just stand on your head.
Okay, what about this one?
Oh, jeez.
That's
You need to
not
just
good.
pop it with your hand.
Like this.
Wait.
Ow.
Wait.
Into the page.
Okay, you can do something like this with your hand if you're double jointed. In order for there to be a force, this doesn't work very well if your hand does it. In order for there to be a force, the magnetic field and the current have to be perpendicular. So there's no force here.
Trick question.
My fingers.
It's very impressive, Abby.
Because they have to be perpendicular.
They have to be, the magnetic field and the current have to be perpendicular.
Let's go.
Guys, you need to be quieter. Alright, questions about any of these? Now we're moving on to charged particles. Remember, it's right hand for positive, left hand for negative.
Right.
Okay, so we've got positive charge, which hand?
Right.
Right hand. So why don't you guys try to figure it out here, don't yell out the answers.
So wait, what is the arrow? Like the positive plus the arrow? Is that your thumb?
Positive, the chart, that's the direction the charge is moving, so that's going to be your thumb.
Okay.
So it is out of the page. Fingers up. The charge is moving to the right. And the force then is your palm going out of the page. That makes sense to everybody? Alright, next one, we've got a negative charge. Left hand. Is the magnetic field into or out of the page here? Into, because it's X's. And the charge is going down, so we're putting our thumb down, fingers into the page.
It's going to the left of the page.
It's going to the left. So like that. So we've got charge moving down, field into the page, palm is pointing to the left.
So X's mean
X's mean into the page, circles with dots mean out of the page. Alright. This time, it gives us the direction of the force, and we need to find the direction of the magnetic field. So which direction are we going to point our palm? Down. And is this left or right hand?
left.
Left. So palm is down, thumb to the right, fingers are pointing into the board, so the magnetic field is pointing into the board. Does that make sense to everybody?
Wait.
So it's off basically.
Alright, so remember we have force this time, so our palm points in the direction of the force. So the palm's pointing down, palm's pointing to the right, and you're looking for the magnetic field, so you need your fingers. Okay. Alright, this one, you have to figure out the sign of the charge. So we have magnetic field coming out, force going up, the particles moving to the right. You have to figure out which hand works. So let's try our right hand first. So we point our magnetic field into the board, or out of the board, I'm sorry, and force is going up, but that does not match the motion of the charge, or the particle. Is that
I told you what happened.
you okay, Kyle? Somebody fell out of their chair in case you're wondering online what happened there.
I hate when that happens. Didn't happen.
Okay. Alright.
Hey, you're back, dude.
Everybody see why the right hand doesn't work?
Yes.
Okay. So our left hand. Force up, magnetic field out of the board, and the particle's moving that way. So our left hand does work, so what's the charge of the particle?
Negative.
Negative. Okay. Does everybody feel like they understand these? Okay. This one gets a little bit confusing. Once we got 3 more to do, then we'll be done once we finish these. And then we're gonna do some more examples of everything. Okay. This time, we're taking a whole wire and pulling it through a magnetic field. And it's moving perpendicular to the magnetic field. Anyway. So, but there's no current in it to begin with. So we need to figure out what way the current's moving. And current we assume is the flow of positive charge, so we're going to use our right hand. To figure out what the current's doing, we need to find the force that the particles in the wire are experiencing. So let me explain this. So be quiet and listen. Let me explain before you guys start asking questions and shouting out things. Okay, so if we assume we have a whole bunch of positive charges in here, which we don't, but that's the way that we assume for current. If we're pulling the wire this way, those positive charges are moving this way. Does that make sense? So because the positive charges are moving this way, we assume it's a whole bunch of positive charges moving. So we take our thumb and point it in the direction the wire is moving. Does that make sense? And then our fingers go in the direction of the magnetic field. So those positive charges are experiencing a force up, and that's going to create a current up. So if you have all those positive charges experiencing a force up, that's going to cause them to move up, and that creates a current that direction. Does that make sense to everybody?
Creates current what direction?
Current is up. Current is up because the force is up. So what gets confusing about this is when you have a wire moving through a magnetic field, you're looking for the current generated. The current is not your thumb anymore. The current is the motion of the particles. And the force becomes current because that force is causing the current. Does that make sense?
So is the wire being pulled that way through?
Wire is being pulled that way through the magnetic field.
You always just follow the way it's being pulled.
Always point your thumb in the direction the wire is being pulled. Abby?
Will current always equal force?
Current is always going to equal force when you're talking about a wire pulled through a magnetic field, and that's generating a current. So if there's not like a current to begin with, then you use the force to figure it out. Okay, any other questions? Alright, let's do another one of these and see how we do. Okay, this time the wire itself is coming out of the page, the wire is being pulled this way. So we take our thumb, point it in the direction the wire is moving, fingers go in the direction of the magnetic field, so like that. So the force is up, so what direction is the current? Up. Does that make sense to everybody? So the current's going up again. Alright, so why don't you guys try doing this one on your own, see if you can figure it out.
Does that, the dots mean this?
That's mean out of the board. So don't yell out the answers, but try to figure it out. So remember, your finger should be pointing out. So we're going to put our fingers like this, thumb down, because the wire is being moved down, and our force is pointing to the left, so the current generated is to the left. Does that make sense to everybody? This is like my favorite test to give you guys because you do all sorts of stupid things with your hands during the test. And last one. So this time you have like the wires going like this. It's being pulled that way, but it's like pointed this way. Does that make sense? So the current's either going to be going into the page or out of the page. So you guys try figuring it out. So magnetic field needs to be down. Motion of the wire is that way. So magnetic field down, motion of the wire is that way. Force is coming out of the page. So what's the current doing? Out of the page. Okay. Any questions on these? Okay, we're going to do a couple of just random practice problems here. Okay, this is what I'm going to do for like your quizzes and tests or some fill in the blank answers here. I click a button and it changes everything. So it changes all the directions and it changes what the answer is. So it's a really good way to practice. So I can make as many practice problems like this as you guys want.
So should we write these down?
No, I have on Edmodo. I made like 13 random put 13 questions on there. I haven't put them up yet, but I'm going to put just a bunch of practice questions with answers on there for you guys. So I would just you don't need to write these down. Let's just go through them together and make sure you guys understand. All right, this one does not have a picture. It has north, south, east, and west. What I would suggest you do is this wall of the classroom is pretty close to approximately north, so just assume that's north, south, east, west. You can also write a little compass on your page. Sometimes they'll help too. So it's going to be north, south, east, west. Okay, so a proton moves north through a magnetic field pointed west. What is the direction of the force that should say proton experiences? I'll fix that right now. So if you see that on a question on the thing, know that it should say proton. Alright. So proton moves north through a magnetic field pointed west. What is the direction of the force the proton experiences? So is this right hand or left? Right. So use our thumb for the direction the proton moves. So like that, since this is north. What direction is west?
Left.
This way. So what direction is the force the proton experiences? Up. That's our answer. You guys want to try another one like that?
Yeah.
Okay. Now it's moving north. So actually, let's do a different one. That one sounded too much like the one we just did. There we go. Okay. Proton moves to up. So up through a magnetic field pointed south.
Wouldn't it be this way? This way.
South. Sorry, I got confused. Proton moves up through a magnetic field pointed south. So magnetic field is pointed south. Proton's moving up. What direction is the force it experiences? East. Okay. Let's try 13 here. Alright. An electron, so which hand? Left. Moves through a magnetic field pointed west and experiences a force up. In what direction is the electron moving? Alright. So take our left hand. Magnetic field pointed west, so that way. And experiences a force up. So our hand should be up like that. So what direction is the electron moving? South, where our thumb is pointed. Alright, let me click it a couple times here, and then you guys... Alright, try doing number 13 on your own now.
I don't remember like what goes with what.
What goes with what thing?
I'm
Yeah,
just gonna
I
label
never-
myself.
Yeah, like I don't remember what the palm is and what the fingers are. and what the thumb is.
Okay, let me give you guys a hint. This is how I remember it for some reason. The thumb is what direction something's moving. That's either like current or anything like that. Magnetic field, I remember because most of the time when you draw magnetic field lines, there are a whole bunch of them, so that you get a whole bunch of fingers. And usually the current or particle is just like one thing moving. So that's how I remember those two. And then force is like if you're hitting someone, you're hitting them with the palm, so applying a force. That is the opposite of backhanding, so that makes
Why,
sense.
Mr. Tente, why is that west on this one?
What? This one? It's possible this got screwed up, so let's check it.
No, that's right.
Okay.
Oh, I went this way, which is not up.
Left hand.
Okay. Everybody, so did everybody get west for this?
Yeah.
Okay. Let's try some. Alright, let's try this one. This is with the wire, so this is the curling hand one.
Wire carries a current south.
Okay, so wire carries current to the south. In what direction is the magnetic field on the east side of the wire? So it's south, so this way. And east is going to be on this side. So it's going to be up.
Can you do that again?
Okay, so wire is carrying the current to the south, so point your thumb south in your right hand. And on the east side is on this side. So like this way is east. So on that side of the wire is pointing up. Does that make sense? Any questions on that one? Brian?
Can
Okay.
we do another one?
Yep. Alright, why don't you guys try this one?
Is this like the other one?
This is just like the one we just did. Okay. Yep, so point your thumb north. Fingers are pointing up at that point. Does that make sense? So the answer's up. Let's try. Here, this is a little slightly different than what we just did. Okay. Wires carries a current to the up. I got all these things that switch. The syntax doesn't always work. But you guys get the idea. Okay, so wire carries a current to the up. On what side of the wire is the magnetic field to the south? So what we need to do is
Left.
point up, and it gets to here, and it's the left side,
Or west.
west. So the answer is west. Does that make sense how you do that one?
North, south, east,
Okay.
and west.
So point your thumbs up, and we need to figure out what our fingers are doing on the west side of this side. The west is over here. So on the west side, we have to figure out where our fingers are pointing to the south. So point our fingers to the south, and that's on the west side of your thumb.
Okay, that makes sense.
Does that make sense, everybody? Alright, let's try one more, and then we'll be done for the day. Okay, a wire carries a magnetic field up on the east side of the wire. In what direction is the current? So we have to have our, on the east side of the wire, the magnetic field is up. So on the east side of our thumb, the magnetic field is up. So what direction is the current then? South. Yes. This is magnetic field. Okay, let me explain this one again. Okay, so the wire creates a magnetic field up on the east side. So we need to point our fingers need to be going up on the east side. Does that make sense? So on the east side of our thumb, and which means that our thumb has to be pointed south. Does that make sense? You guys want to do any more of this, or you feel okay? Feel okay? And I'll turn off the camera.
Come on up.